Hello, in this session we will discuss about the use of postulates of quantum mechanics to understand the behavior of a quantum mechanical particle in one-dimensional box system. So basically in the last sessions we have discussed postulates of quantum mechanics. So basically there are two major postulates. One is probability density and the time evolution of states, and the one other major postulate was expectation value of any observable. So we will discuss these two quantities, that is the probability density and the time evolution of states and expectation values of various observables. First we will discuss probability density and time evolution of state. The probability of finding a particle in small interval dx is given as psi star into psi dx, where psi the wave function psi star or psi is a function of both position and time. So the complete wave function is defined as product of a spatial part and a temporal part. The spatial part is a function of the spatial wave function is function of only the position, and the temporal part is given as e to the power minus I e t over h bar. This En is the energy of the corresponding state. For the first state it will be E1, for second state it will be E2, for third state it will be E3. So these various states, the energy of various states and the wave functions associated with various states we have discussed last session. So if we multiply the spatial part and temporal part, we will get a complete wave function. Now this when this wave function and its complex conjugate is multiplied over a small interval dx, that gives us the probability of finding a particle, or this quantity is called probability. Now the probability is given as this psi star into psi dx. This is probability. Now the psi is a function of both position and time. So if I write that the spatial part and temporal part taken complex conjugate, again the spatial part and temporal part of the wave function and dx, then if I do that, then this e over r is there is a complex quantity. This iota quantity is the complex quantity. That minus sign gets converted into positive sign when we take a complex conjugate. Here this star should not be there. After taking the complex conjugate, this minus i has been converted to plus i. This star mark must be omitted. So now there are two different exponential. One is e to the power I e t over h bar and e to the power minus I e t over h bar. When they are multiplied, they will be giving 1. So what I am left with, the probability is psi star x psi x dx, means both the wave functions, the product of two wave functions, the product of wave functions and its complex conjugate, but this wave function is independent of time and it depends only upon the position of the particle. That gives me the probability of the particle. So I can say that although the state function, the total state function or total wave function is dependent on time, but the probability is time independent. Although the state function, that is psi xt, is dependent upon time, but the probability is independent of time. In addition, if we take probability density is nothing but psi square. So if I take probability density also, that will be also independent of time. So probability of finding the particle in a region dx does not change with respect to time. Therefore such a state is called stationary state. Now we will take a special case. In this condition, in the condition discussed just now, we have taken only one state function and we have found out its probability and probability density, and we observed that this probability or probability density both are independent of time. But we will take a special condition, special state. In the special state, the wave function is a linear combination of two different states. Suppose the two states are psi 1 and psi 2, and their linear combination is given as psi 1, that is the spatial part, multiplied by the temporal part, which is e to the power minus I e t over s bar, plus psi 2x into e to the power minus I e 2 t over h bar. So this is the first state, and the second term is the second state. So we have taken a linear combination. When we take a linear combination, we have to multiply suitable coefficients. Suppose the coefficients are c1 and c2. For simplicity, let's assume that the coefficients are 1. Both c1 and c2 are 1. The linear combination ideally should be c1 psi 1 plus C2 psi2, and we are assuming that the coefficients are 1, and this 1 over root 2 is a normalization constant for this linear combination of two states. Now we are assuming that the wave function of a quantum mechanical system is a linear combination of two different states. So what will happen for that situation? Now when the wave function or the state of the quantum mechanical system is a linear combination of two different states, then there is both spatial part and temporal part is there. If we use this state, if we use this linear combination of states, or if we use this new state and we apply the time dependent Schrodinger equation to this new state, so instead of psi n I will write this linear combination of state and use the expression of time dependent Schrodinger equation. What is time dependent expression for time dependent Schrodinger equation? It is I h cross d over dt minus h bar, or the Hamiltonian operator, and that whole of the operator acts on the wave function. And what is the wave function here? The wave function here is the linear combination of two states, and that should be 0, that should be equal to 0. If this condition is satisfied, this is the time dependent Schrodinger wave equation. Actually this linear combination of states will satisfy if we substitute psi n with this linear combination of states, then this condition will be satisfied. But it is important to note that for any linear combination of states, that it will obey the time dependent Schrodinger equation, but it is not a stationary state. Means it will not be independent of time. We will see how it is not a stationary state. In the previous case we considered when there is a single state, only one state, that was a stationary state, means the probability was independent of time. But when we are taking a linear combination of states, we are saying that the state is not a stationary state, that is the state will evolve with respect to time. Now as I said, it is a linear combination of states, so the new state psi a psi xt is 1 over root 2, which is a normalization constant, the first state and the second state. So if we take probability density, suppose we want to take, what is probability density? The wave function and its complex conjugate multiplied by the wave function multiplied by with its complex conjugate. So if I do that, 1 over root 2 and 1 over root 2, that gets 1 over 2, and there is the first state complex conjugate and the second state. So if we multiply all the terms and rearrange, we'll get 4 terms. We'll get first 2 terms which are time independent. The first term and the second term are time independent, whereas the third term and the fourth term are time dependent terms. So what does this mean? This means the probability density of a linear combination of states. The probability density of a linear combination of state is time dependent, because two states are time independent and two states are time dependent states. Two parameters are time dependent parameters. So in general the probability density is time dependent. But in the previous case, when we consider only a single state, in that case the probability or the probability density was independent of time. So we have already shown that for a stationary state, for any particular stationary state, probability density is independent of time. We have seen that in the first case. And for linear combination of states, the probability density is time dependent. Here time dependent terms are appearing. The third and fourth term are time dependent terms. So when the state or the wave function of the quantum mechanical particle is linear combination of different states, then that such a state is not a stationary state. Rather the state will vary with respect to time. But when there is only only a single state is there, only a particular only a single state is there, then that particular state will be a stationary state and it will be independent of time. So linear combination, when we take linear combination of different wave functions, then those the resultant wave function is not a stationary state. Therefore linear combination of state is not a stationary state. The probability density of a linear combination of state changes with respect to time. These are the time dependent states. Now what is the physical application of this time dependent and time independent things? In laser, suppose a laser beam is passed through a sample solution. Laser means light amplifies stimulate emission of radiation. So when laser beam passes through a sample, Eigen state different particles get disturbed, and the new states are linear combinations of stationary states, and those states evolve with respect to time. Before the passing of the laser action or being, the stationary states don't the states of particles are said to be stationary and they don't evolve with respect to time. But when we pass a laser beam through the sample, the states get disturbed and result in linear combination of various states, and they evolve with respect to time. Now, another important property we studied in postulates of quantum mechanics was expectation value of operator or average value of an operator. So we take expectation value to find out for a particular observable. Various observables that we have discussed is energy, position and momentum, all those observables we have discussed. So we will discuss those observables here and find the values of those observables. So the expression for expected value that we studied in postulates of quantum mechanics is expected value of an observable A. Suppose the observable operator is A corresponding to any observable A. So the expression is psi the acting on psi, the wave function dx over psi xt dx. The states or the wave functions normalized, the denominator will be equal to 0 because it is essentially the normalization condition. The denominator condition is nothing but the normalization condition. So when the wave functions are or the states are normalized, denominator will be 0. But it is important to note this psi is function of both position and time. Position and time constants. That wave function is a product of a spatial part and a temporal part. Temporal being e to the minus e over h bar. En means the energy of the particular nth state, and sin x is the wave function of its state. So substituting the spatial and temporal part, my expression for expectation value of an operator A looks like this, and now the operator is there only in the numerator and the operator is absent in the denominator, and then as I said, in the denominator there is a complex to areas complex char should be not be here because I have taken complex conjugate. So if I take complex conjugate, minus I becomes plus, so I t over bar there will be equal to 1. So I am left with psi n star x into psi n x dx. The new part. Now wave function normal will become equal to 1. Now what happens in this case of denominator? Now what case of numerator the operator is there, we simply cannot multiply e to the power iet over h bar and e to the power minus iet over h bar because there is a operator acting on the exponential. For special operators like Hamiltonian, position, all these kind of operator, the operator itself does not depend upon time. The operator, position operator, momentum operator, they are independent of time. This exponential will be free from this operator. This operator will not act upon this exponential because this exponential is a function of time. So when we are considering position and momentum operator or Hamiltonian operator, we can take the exponential out of this operator and we can multiply with previous exponential and we get a value of 1. So what will be the numerator now? The numerator becomes psi star x operator which acts on the wave function, that is psi x dx. Psi is only function of position, not of time. So now my expression value is integration over whole space psi star x operator psi x dx. In the denominator part, integration over whole space psi star x psi x dx. When the wave functions are normalized, denominator becomes 1. So we'll with this expression, so the expression is time independent for certain operators like Hamiltonian, for operators which time independent, or operator which is not a function of time. For such kind of operators, the expectation value of the particular observable, corresponding observable, will be independent of time. So with that we will discuss position movement operator. What is the expectation of value of position? Expectation value of position for first Eigen state. Expected value position for first Eigen state. Eigen state complete solution, that is the wave function is a function both position and time. But we have seen that position operator for position is multiplication of x, and x independent of time. Position operators, the expectation value is independent of time. So I will write my expectation for position is in form of time independent parameters, time dependent wave functions, because the position operator is independent of time. So the total function is reduced only to spatial parts, and my integration limits are 0 to L because I am considering particular one-dimensional box. So my integration limits are 0 to L. Now what is Eigen state for first Eigen state function, first Eigen state, or the value of first Eigen state for particular one-dimensional box? Discuss last session is over 2 over L sin pi x over L. It is actually sin n x over L. N is 1 for pi Eigen state, n is equal to 1. So the wave function for pi Eigen state is over 2 over L sin pi x over L. And I will substitute my 1 x value or the function value, the expectation in the expression value expression. Now this wave function is normalized. Normalized constant is normalization constant is root over up by L. So the wave function normalized the denominator normalization constant. So consider the denominator anymore. I am directly considering the numerator, and the numerator again the phi against I am substituting state value. So There is eigenstate, take its complex conjugate x, then the eigenstate. This is not complex, so it will affect the eigenstate. So I am left with x sin square pi x over L dx. Now what is square theta? I will use trigonometric identity 1 minus cos 2 theta over 2. And if I do the integration, if I go ahead the integration here and here, over of 2L over L, and that will give 2 over L, and it comes out of the integration. And if I say the expectation value position is equal to L by 2, means the wave function is symmetric with respect to L. L is L by 2. So for first eigenstate, the expectation value for position of the particle is L over 2. What does this mean? Means particle will be found at the center of the box. L by 2 means center of the box, and that is correct. In the last session we have discussed that the probability of finding the particle for first eigenstate is at the center of the box. Similarly, if we substitute the second eigenstate 2 pi x over L, for third eigenstate it will be 3 pi x over L, and we substitute this second or third eigenstate expression in the expectation value of position, will get those corresponding expectation values for second and third eigenstates. This L by 2 is expectation value for position of the quantum mechanical particle in one dimensional box for first eigenstate. For first eigenstate is important because we are using the wave function for first eigenstate. Now expectation value for momentum, instead of position we will be using momentum operator. Here again the wave function is normalized, that's why the denominator term is 1. We are not considering the denominator, and we are directly using our expectation value expression here, and the denominator is 1, and instead of operator I am using for momentum operator. What is momentum operator? Minus IH bar d over dx, that is the momentum operator. And what is the wave function for first eigenstate? Suppose I am considering the first eigenstate psi 1, then here I have written psi 1 star and psi star, psi 1, but suppose we are considering nth state, the general nth state we are considering, then the eigen function, the eigenstate for nth state is root over 2 by L sin n pi x. I am repeating, I am considering the general nth state. I am not considering any particular state. That's why I am taking sin n pi x over L. For first state it will be 1, for second state it will be 2. So the first eigenstate, its complex conjugate, the operator, the second eigenstate. So if I do the solution, if I take the constants out of the integration, then d over dx sin x will give me cos x. Now again one more constant I will take out of the if I solve the integration, I will be getting 0. So the momentum operator, be it any state, be it ground state, first state, second state, third state, be it any state, I will be getting the expectation value for momentum is 0. Upon solving the expectation value expression for momentum, I am getting 0. Without doing this calculation also, I can say a particle when it is confined in a box, it has probability of going forward and backward. So when it does a number of motion, the forward motion is positive momentum and the backward motion is negative momentum. So essentially net momentum will is 0. That's why without doing calculation also, we can say that the average value of momentum of a particle confined in one-dimensional box is 0. So this is all about expectation value for momentum operator. Now expectation value for momentum square. The momentum operator was minus IH cross d over dx. Now the momentum square operator is, we have to take square. So if I take square of this operator minus IH bar d over dx, what I will be getting? I will be getting minus h bar square d square over dx square, or dou square over dou x square. Because we are considering only one dimensional box, I can only also write d square over dx square. No need to take partial differentiation because there is only one variable. So I can also write d square over dx square. So what is my momentum operator expression? Square of expectation value for momentum square. So there is again I will take the first eigenstate, that's why I am writing psi 1 star x and then momentum px square psi x dx. So instead of psi 1 star x, I will write what is the wave function for first eigenstate, root over of 2 by L sine n pi x over L. So 2 by L goes out of the integration. There are two root over of 2. There are two root over of 2 over L. So the net if I take square, then it will be 2 over L, and that comes out of the integration. Similarly h square is also a constant, minus h bar square is also a constant, it comes out of the integration. Within the integration I have sine pi x over L into d square over dx square sine pi x over L dx. Now what will be this term, d square over dx square sine pi x. So the double derivative of sine theta will be again negative of sine theta with respect to some constant terms. The theta constant terms are there. So my the momentum square expectation value becomes, if I substitute this one in the integration, I'll be, and if I'll solve that, I'll be getting h square pi over L square 0, and the integration limits are 0 to L, 2 over L sine square theta, or here theta is pi x over L. Now 2L sine square pi x over L is nothing but the wave function. What is the wave function? The wave function is, what is the expectation, the eigenstate? The eigenstate is root over of 2 over L sine pi x over L. So here in the integration I am getting 2 by L sine square pi x over L. What does this mean? This means psi, the wave function in the first eigenstate. So or the wave function of the particle in the first eigenstate. So in that, within the integration I have psi 1 square x, because this expression is nothing but psi 1 square, because my psi is what? Psi is root over of 2 over L sine pi x over L, that is psi 1, and here sine square is there plus 2 over L is there. So this means this is psi 1 square, this is psi 1 square, psi 1 square, this is psi 1 square. So and that is integrated over 0 to L, and again there is a dx term is missing here, the dx term will be there. So 0 to L or the over whole space, particularly in one dimensional box, means the length is starts from 0 to L, and this is psi 1 square x So what does this mean? This is a normalization condition. So this will be 1. This integration term will be 1 because that will be normalization condition. This is the eigenstate for ground state integrated over whole space. That will be 1. So 0 to L psi 1 square x is equal to 1. So this integration term is nothing but psi 1 square x, and that is integrated over whole space or total length of the box, and that is 1. So what I am left with? I am left with, here dx is missing, please add that one. So I am left with the expectation value for momentum operator square is equal to h bar square pi by L to the power square. So if I rearrange, I will be getting px square expectation value or average value is equal to h bar square pi square over L square, or pi h bar square over L to the power whole square. That will be my expectation value for momentum square. Okay, this is for fast eigenstate when n is equal to 1. For what will be the expression for n is equal to 2, n is equal to 3, n is equal to 4? We have to substitute the corresponding wave equation. We have to substitute the corresponding wave equation in the expectation value expression, and if you do that, we can find out that the expectation value for any other state or any other eigenstate is given as n square h square pi square over L square. For if it is a ground state or fast eigenstate, n will be 1. For second state, n will be 2. Like that it goes. So this is all about the expectation value for momentum square. Now what is the expectation value for kinetic energy? Kinetic energy, according to classical physics, we know kinetic energy is given as p square over 2m. P is the momentum operator, p square over 2m. Recently, just now we deduced an expression for p square. So if we use that expression and divide by 2m, m is the mass of the quantum mechanical particle, then we will get an expression for energy, and this expression comes out to be n square h square by 8 ml square. If I substitute this h bar as h over 2 pi, I will be getting n square h square over 8 ml square, and the energy expression is same as the energy eigenvalue that we have obtained in last session. So our average value of kinetic energy also matches with the energy expression that we obtained in the last session. With this, I will stop here. In the next session, we will discuss particle in 3-dimensional box. Thank you.